All right. So we've been talking about how adding solute to water, or to any other solvent for that matter, changes its boiling point and changes its freezing point. Fred, do you remember how adding salt to water changes the freezing point of the water?
Let's see. I know that if you put salt on ice, it changes the freezing point of the salt water solution, or the water, right?
Yes. Adding salt to ice melts the ice because it changes the freezing point of the water, the resultant solution. Does it lower that freezing point or raise it?
Well, you can freeze salt water, but you need to get a lot colder. So the ice thaws because the freezing point is lowered.
Okay, so you're lowering the freezing point of a solution by adding a solute to it. What about the boiling point?
Adding solute to water raises the boiling point.
Very good. So here's a question about a 5% glucose solution. Has a density, 5% glucose solution has a density of 1.05 grams per milliliter. What's the expected boiling point?
Expected boiling point. Okay. I'm not exactly sure. I don't remember how to do this.
Well, okay, so they provided this. What is this business here, this KB?
Looks like some sort of constant.
Yeah? What's the best thing we can do for this sort of thing?
I think we were saying look at the units, right?
That's right. So it says 0.51 degrees per, what's this little m?
That's molality.
All right. So we're talking about a change in the boiling point, okay? And we have this constant that says 0.51 per molal.
Okay, so yeah, so that's going to be the shift. So we just have to find out the molality of our 5% glucose solution.
Very good. So we have to find out the molality of the 5% glucose solution. So what does 5% mean?
Well, it doesn't mean 5 molal. It means like 5 grams of glucose for every 100 grams of solution.
Very good. So 5 grams of glucose for every 100 grams of solution. All right. Now, if I have 100 grams of solution, can I identify how many liters that is?
Yeah, well, we got the density, thank goodness, so it's 1.05 grams for every milliliter.
All right. So if I want to convert that to milliliters, 1.05 grams for every 1 milliliter. So 100 divided by 1.05. And that is how many milliliters, or if I divide that by 1,000, right, that'll give me how many liters. So 0.0952 liters of solution. Now I just need my grams into moles to get it into molarity. But I guess I don't want to go to molarity, do I?
No, you want to go to molality.
So I don't want liters of solution, do I? I just want kilograms of solvent. Kilograms of solvent. So if I have 100 grams of solution, that's made up of 5 grams of glucose and however many grams of water, right? So that means 95 grams of water.
Okay, 95 grams.
So I have 95 grams of water. That is 0.095 kilograms of water, agree?
Yeah, I agree with that.
So now I just need my moles of glucose over my kilograms of water, and that should give me my molality. All right, so 5, looks like the molar mass of our glucose here is 180. So 5 divided by 180, 0.027, that's moles, and moles per kilogram of solution divided by 0.095, that should be my my molality, right? So 0.292. Now what do I do with that?
You multiply that by 0.51 degrees per every molar.
Okay, very good. 0.51 degrees for every mole hour. So it's only increasing like 0.15 degrees. So 0.15 degrees Celsius. Now, is that the new boiling point?
Oh yeah, I guess. Well, it's not one of the ones that's up there.
So that is not the new boiling point, is it? It's the shift, isn't it?
Oh yeah, okay, it's the shift.
So if the shift is going to be 0.15 degrees, it's going to be, our answer is going to be 100 plus the 0.15 degrees.
So it's 100.15. I guess that's probably only 3 significant digits, so it's probably not going to change much, is it?
That's right. The resulting temperature, there's not going to be a significant change in the temperature simply by having a 5% solution of glucose. Okay. Osmosis. I think you guys have heard about osmosis in biology classes, and we're not going to talk a lot about osmosis, but osmosis, the relationship between osmosis and the resulting concentration of solution is what we call, or is dependent on molarity. Osmosis is the motion of a substance through a semi-permeable membrane, and almost always we're dealing with water. And when we have a concentrated solution on one side and a dilute solution on the other side, the semi-permeable membrane, meaning it's only permeable to certain compounds, and again, usually that's water that it's permeable to, water is going to move across the membrane in an effort to make the resulting concentrations the same. Now, if you look at this sort of a scenario here, concentrated solution on the right, dilute solution on the left. As we said, if this container is sealed, molecules will evaporate up and also molecules will condense down. Well, the rate at which molecules will evaporate away here will be higher because there are more solute molecules here, more intermolecular forces that need to be overcome for the water molecule to leave. All right, more higher mole fraction of compounds that have zero volatility. Right, that's how we were discussing previous slides about the net or the resulting vapor pressure is related to the mole fraction and the resulting, or the vapor pressure of those different compounds. So if you have two solutions like this, water will continue to leave this solution. Water tries to leave here, but it can't happen very quickly because of the intermolecular forces. So water constantly leaves here, and then as it lands here, it'll have this container here will have a stronger affinity for it because when the water molecule lands, it has lots of intermolecular forces that hold it tightly. All right. This is an interesting method for slowly concentrating a solute in solution. So here is a drop, and this represents this little red drop on top of this cover slip. All right. What we have here is what we call the hanging drop method, and we have down here a reservoir that is relatively high in solute. Here we have a drop of solution that's relatively low in solute compared to the reservoir. And so what happens then, again, as water molecules leave here, instead of, there will be an equilibrium in which they'll be able to come back, but because this is a higher concentration of solute, more of the water molecules are going to want to gather into this reservoir down here. So this drop, which again represents this over time, and so this is a video, we'll watch this. This drop over time, the water molecules leave, which slowly, gradually concentrates the solute inside. And this slow concentration, this slow process, allows those solutes to gradually form solids in such a way that the crystals form very ordered and slowly. Okay? And so you see all the different solutes here that are in this drop, in this solution. And you can tell how many there are based on the different shapes of the crystals, because generally different solutes are going to have different shaped crystals that form. All right? And so this becomes an effective method for creating crystals. Now, do you remember why we like to have crystals?
They're magic.
That's right, they are magic. They're magic in that you shoot X-rays at them, and the diffraction off of those crystals gives you information about the actual molecular and atomic structure of the atoms and molecules in those crystals. Okay, very good. So, here are some vocabulary words that are nice to be aware of, especially if you're going into medicine, right? If you're going to be a nurse, or think about IVs, right? We give people IVs because we need to maintain their hydration level, right? If we give intravenous fluids that is too high in salt, then that will pull the water out of the blood cells, and you'll have a hypertonic, you'll have a hypertonic medium, and you'll have a contracted blood cell like this, a shriveled blood cell. If it's the correct concentration of ions, isotonic, the same concentration of ions, then your blood cell will look like this. If there is not enough salt, then the blood cells will expand and eventually burst. So you need to make sure you have the right amount of salt in your intravenous fluids so that it doesn't change the ability of the blood cells to survive and be active. All right, and here's our equation for osmosis. The osmotic pressure is related to the molarity times our ideal gas constant, because, again, the osmotic, or the value for osmotic pressure is in terms of pressure. So we need to have a way to get a gas constant in there that can allow for moles per liter and temperature, and then we can identify what the resulting osmotic pressure will be given the conditions here. Dialysis, you've probably heard of dialysis. It's where we take, usually it's going to be a patient's blood of some sort, right? Fluids, and we're trying to remove from that blood small molecules, specifically, relatively small molecules. I shouldn't say relatively small molecules. We're trying to filter out larger molecules and leave behind the smaller ones. And specifically, what we're trying to filter out is sugar, right? Trying to get sugar out. But this is done over a semipermeable membrane again, and this occurs through osmotic pressure. We have to apply that pressure to get dialysis to work. Okay, now we've talked about how the resulting molality of a solution will change the concentration, the boiling point and melting point of a resulting solution, right? So we said, for example, if I have a solution which has 300 grams of sodium chloride for every 1 liter of solution. If I calculate the molality of this and I know my constant, right, I can identify the change in temperature. Change in temperature, whether it's change in the boiling point or change in the freezing point. Remember that?
Yeah, we just did that.
Now, one thing that we didn't mention that we have to recognize is that if I put in 300 grams of sodium chloride into solution, I could take that 300 grams divided by 58.44. There we have 5.1 moles, all right, 5.1 moles of sodium chloride, all right, and then I could identify with the density, find out how many kilograms of solvent I have. But the thing that I need to also take into account is that when I put 5.1 moles of sodium chloride, I end up getting 5.1 moles of sodium and 5.1 moles of chloride. And so this is called a Vant-Hoff factor, and it needs to be put into our equation, our relationship between the change in temperature, the molality, and our K. We need to put that into our equation right there, that I value. And what that's saying is how many substances or how many actual entities end up being in solution. If I put 5.1 moles of sodium chloride into solution, I end up with 2 moles of ions, 1 mole of sodium and 1 mole of chlorine. All right? And so that delta, that change in temperature, is going to be whatever the molality of the sodium chloride is times 2, and then multiplied by our constant. Okay? So if I have 5.1 moles of sodium chloride and 5.1 moles of sugar placed into water, so let's set up our little idea here. Let's just do 2 moles of NaCl and 2 moles of C6H12O6. All right. Into these solutions, same volume of solutions, so both of them have 1 liter in here. All right, actually I should say 1 kilogram of water. 1 kilogram of water. So now we essentially have not just 2 moles, but 2 molal of both of these solvents, or solutions. Which one will have a higher boiling point? Which one will have a higher boiling point?
So I think what you're saying is the sodium chloride will, because the 2, well, because there's 2 ions, sodium and chloride ions,
right?
Then that I value becomes 2, and you double the amount of actual solutes floating around.
That's right. That's right. So let's see if we can solve these problems then. We're making pasta. We have 15 grams of salt, and the solution is brought to a boil. What is the boiling point of the water?
15 grams of salt.
Yep, 15 grams of salt, and in 2 liters of water.
So 2 liters, that's 2 kilograms, right?
That's right, 2 kilograms of water and 15 grams of salt, so 15 divided by 58.44, so 2.256 divided by 2, that means our molality is 0.128 molal.
Yeah, the boiling point was 0.51, right?
That's right, 0.51 degrees Celsius for every molal times 0.51, so 0.065. So the expected boiling point, instead of 100 degrees, is going to be 100.065. Okay, we added that on, right? Now, what about you run out of salt and you put the same mass? Oh, whoops, I forgot to 0.065. I need to multiply that by 2 because there's 2 units of sugar, so it's 0.1 here. So it's 100.1 degrees Celsius. So that part is where? There it is, 2 times 0.123 times 0.51. Okay. So, in our second question here, suppose you're out of salt. What mass of sugar needs to be added to 2 liters of water to raise the temperature, the boiling point, by 0.1?
So you want to raise the temperature by 0.1.
Very good. That's right. 0.1. That's going to be your change in temperature.
So the mole the T could be solved. 0.51 is the degree Celsius per mole.
All right. So now we need to have our molality here, right? 0.1 divided by 0.051. So my molality needs to be 1.96. All right. Now, my molality here for my sodium chloride, I'll go back to that one really quick. The resulting molality was only, let's see here, 0.1, 0.256 was the resulting molality. Okay, here I'm going to need to get a molality of 0.196. Oh, that was my problem here. It wasn't 0.051, it's supposed to be 0.51. So this should be 0.196. So 0.196 is the resulting molality. Okay, and to get that, that's how many moles I need. And I need to have 2 liters of solution. So I need 0.196 moles for every kilogram. So I just need to multiply that by 2. I have 2 kilograms of water. So 0.392. That'll be the moles. Oh, but then it's asking what mass. So times 180. So I'm going to need 70.5 grams of, whoops, I made a mistake there. Let's see, 0.392 moles, and after I have 0.392 moles, oh, sorry, this was not glucose, it was sugar. So instead of multiplying it by 180, I need to multiply it by 342. Okay, very good. 2 significant figures. All right, so take-home message, we can change the boiling point or the melting point by adding solute. If we use a salt, like sodium chloride or potassium bromide or sodium carbonate, we have to keep in mind that the change in temperature will be modified. The molality times our constant, right? Whatever constant, boiling or freezing. But there's going to be this Vant-Hoff factor that's related to the number of ions that may result if this is a salt. Okay, so here's one question for you. If I have 1 molal of solution for each of the following salts, which will have the highest boiling point? Sodium iodide, copper nitrate, copper carbonate. This is going to be copper 1 carbonate. Oops, not copper. Sorry, other way. Copper carbonate, Cu2CO3. Or sodium bromide. Okay? 1 molar solution of each of these, which will have the highest boiling point. Okay?
Well, if they're same 1 molal of each of them, won't they have the same?
Okay? But remember that when you put 1 molal of each of these into solution, then you have different amounts of ions that actually dissolve.
Oh, okay, I see. So in the first one, you got 2 moles of ions.
That's right. So 1 molal of solution, that would mean 2 molals of entities, ions. How about this one?
That's 3, right?
That's 3. And this one?
Oh, that's 3 also.
Well, here's one thing you need to look at for, let me rewrite this, copper 1 carbonate is its solubility. Do you know if this is soluble?
Oh, yeah. That's not going to be soluble.
That's right. That's right. So kind of a trick there, and that really wouldn't be something we do. But the idea is you have to recognize that these things have to be soluble, or it's because of their solubility and dissociability that you get the shift in the boiling point here. And so this results in 2 ions as well. So we got 3 ions and 2 ions, and the answer will be this will make the largest shift in the boiling point because it has more ions. Okay, good job, Fred. Good chapter.